And I'm going to fire Grasshopper up immediately after that. And so I could have done this like ahead of class and then like given everyone the family or the thing that changes, but I don't think that's as much fun. And I'm also going to show another way to do this, maybe next class, where instead of using, we'll have pretty much a family in Rhino or a family in Revit and our geometry in Rhino. And so our family in Revit can then be also getting manipulated by the radiation analysis. So we'll have like kind of two tandem streams of information coming out of that random or that radiation analysis, which should be fun. And then also give everyone a little more exposure to like families in Revit, which are like the backbone of Revit. Being able to author a good family is a super valuable tool that actually, unfortunately, not a lot of people have right out of school. So that could be something else, can bolster yourselves up. So I'm actually going to do two things at first. First, I'm going to make just kind of a wacky wall that we're going to use for like our skin. And then the second thing we're going to do is we're going to make just one like module of what we're going to populate that skin with. We're going to flex that module to make sure that it's kind of flapping around or doing whatever we want. And then we're going to apply it to the surface and then use the radiation analysis of that surface to then inform that geometry. So it's like smart in geometry. I think there's a really cool blog called Informed Geometry or Informed Geometry, worth looking at too, but not directly related to this. So I'm just going to freeform out something super weird maybe. Yeah, that looks like fun. And then if I hold Alt and I drag up, I'm going to get another one. I'm going to turn the control points, or I guess I don't have to turn the control points on, but I'm just going to manipulate this upper curve a little bit as well and try to get something a little more funky out of this. Maybe I'll take this guy and flip him. Okay, and then I'm going to reference in both of my curves now into Grasshopper. And I'm going to open up bifocals so we can look at the decals and the names. So I'll right click on that curve, go down to set one curve, and then I'll click on that curve I want to reference in Rhino. Do the same for the lower one. Set one curve, lower curve, and then I'm going to loft. Actually, I could either loft these. Otherwise, if I come in here to surfaces now that I have both of my curves in here, there's another type of surface that we can create under primitive. No, not under primitive. I think it's under freeform. And it is a ruled surface. That's what I was looking for. So that essentially is a surface between two curves. That'll fit what we want to do pretty well here. So here we've got a little bit of a weird shape. We could do a loft and just see what the difference of that is. So if I go to loft and I'll hold shift while I drag these in to add two at a time, you can see they're almost identical if they aren't identical. The only nice thing about loft is if we wanted to add like a third level to this and make it like super noodly, we could do it with that, and that might actually be fun to do. So I'm just going to add a third one in, and see what this looks like. It might not be that cool. That's our bottom one. This is our middle one. I'm going to bring one more curve. Say set one curve. Do that. And then if everyone remembers, the way that I'd like to handle the loft is by using a node called merge. And what this will let me do is make sure that I'm bringing those curves in the right order. And I'll show you the reason why that might not work. So if I just add this one in, we can see we're actually getting like two surfaces, or what appear to be two surfaces. And what's happening is it's going from the top to the bottom and then back up. So it's making like a weird connection there. So if I bring it in this way, I can make sure that the list or the order of these is the way exactly how I want them. And so that makes a little bit more sense to me. Great, so now we have like our boundary surfaces. So I'm actually going to come into my layers, bring this out a little bit. Oh, am I hiding it? I guess so. Just going to hide that default layer. And then I'm going to hide these curves so I just have my loft. Hide. And I got there by holding Control and hitting spacebar for our quick wheel. So now we're going to figure out how we're going to like panelize this surface. I'm going to use a plugin called Lunchbox. Does everyone have Lunchbox? Does anyone not have Lunchbox? Cool. Okay. Lunchbox has a bunch of really fun. Lunchbox is somewhere. There's Lunchbox. I need to maybe call out some of my different tools here. And I think I'm going to grab Triangle Panels B. Seems like a pretty good place to start for what we're trying to do. And I'm going to bring in my lofted surface for that. And I'm getting a bunch of weird artifacts here. So I'm going to change my U and my V divisions to something quite a bit higher, give myself a little bit more resolution. Bring this one in now as well. Kind of, actually, I want to change my V divisions to look a little bit better. Okay, so that's, maybe not the most seductive thing that I've ever seen, but I think it'll work. Again, the fun part is later we can play with this after we run the radiation study on it. We'll be able to like manipulate that base surface and then watch everything kind of respond as well. And that'll take quite a bit of computing power, so it's not going to be as fast as where we're at now. Is everyone kind of here so far? Okay. And if this class ends up, if we only get to like having the component done, I think that'll be okay. Because again, next class we'll be looking at both this and Revit kind of at the same time. Hopefully bringing everything full circle, where we're using Grasshopper, Rhino inside, environmental analysis, and manipulating our geometry accordingly. Sounds fun, hopefully. Great, and then so next thing I want to do is I want to see, so if I'm going to be changing this geometry, I can figure out like a couple of different ways to do this, and all right, I'm just going to trace it with my mouse. But as we can see here, we have a bunch of what look like triangles, but we actually have like a hexagon within that. So there's a couple of different ways we can kind of break this shape up, but what I want to just double check is what the list order of each of those panels are. Because if I'm looking at this edge and it goes like 1, 2, 3, 4, 5, and then 6, 7, 8, 9, it's going to change my data list from what I want, or maybe from what I want to something that I don't want, or the other way around. So in order for me to do that, what I'm going to do is I'm going to get the centers of these panels and then use a point list to see what that list actually entails. So if I go to area is a quick win to do this. It is a little bit more resource intensive, but it ran. And then I'm going to use a centroid to go to point list. Point list here, and I'll bring those into my points. I can hide my centers to give myself a little bit better view here. And now I can see that I don't have a very nice, I don't have this broken up the way that I want it to, right? So it's actually going like 1, 0, 1, 2, 3, 4, 5, comes all the way back around 75, 76, 77, 78, right? So it's like striping these into rows. And what I want is like an actual hexagon with all these triangles in it. So I want something quite a bit different. And I think I can get there by going into dual graph, which is from Weaverbird. And if we don't have Weaverbird, does everyone has Weaverbird so far? I think we've used it a few times in class. Okay. And we bring this in, it's gonna say no. Oh, because we actually need the edges of those panels and not the surface of the panels, if that makes sense. Another way, we can also get there another way by going into our hexagon cells is another type of panel that we could use. So I'm actually just going to plug that in and see what that one looks like. I'll hide this, use the same U and V divisions. And that gets us a pretty nice hexagon cell, except for I still have these edge ones that I don't like, that are only like a half of a hexagon, which is going to mess up like our individual, which ones we actually want to use. So I'm going to go to my surfaces, I'm going to go to analysis, and I'm going to get my edges, my B-rep edges. And then if I hover over this, I have a list of 3 edges. This is interesting. We have, because we're using the same U and V, we have a pretty nice relationship between our hexagons and our not hexagons with our triangle panels, but it's not quite perfect. So I'll delete these out of there. And then I'm going to take a panel just so I can look at what's inside of my edges here. We can see I have a list of 3 different lines, and those are corresponding to the 3 sides of each one of these triangles. So I can join those by saying join curves. And now what I get is just a single curve for each one of those triangles. There is another way to get that that's without using B-rep edges, but for the purpose of this will work fine. And then we can plug these in and flatten them. And so the reason why I like this method is we can see that now we have our hexagons, and I'm actually going to flex this a little bit differently. Oop, too far. Now we have our hexagons, but none of our we only have full hexagons. We don't have edge partial hexagons, if that makes sense. So in terms of manipulating everything here, this I think will work pretty well. I can hide my points now because I'm not using that. And if I wanted to, I could even hide these other edges and see now my hexagon surface that's just hexagons, which is kind of nice. No half hexagon. So then I have to figure out some type of logic of how I want to manipulate these hexagons. If I'm thinking about them as a surface, is one way, but I want to think about these as almost like a bunch of little pieces of pie inside of a hexagon, but then have the ability to like open and close according to a radiation. So I'm actually going to leave my point list in here. I'm just going to hide it so that later on, if anyone wants to kind of deconstruct this, it'll hopefully make a little bit more sense. So now I'm going to open up another panel and just double check to make sure that there's not a whole list of, I want to see the kind of data tree of each one of these. So yeah, so it's giving us like a polyline. So I'm going to get just one item, list item, list item, there we go. And I'm doing this, if we remember kind of, again, the panelization stuff, is I just want one of those nodes to then manipulate. And we can see here that it's a full hexagon, so this is a really nice way to go about this.
It crashed.
Oh, I'm sorry.
It's gonna scream. I'm sorry.
It's all right. If it literally starts screaming like a goat, then might have to take it out. But
Thing for a second. I just have to
no,
say, okay,
that's
once
fine.
it does it, but
That won't mess us up too much. Sorry you're having to deal with computer troubles while we're working on the computer. Okay, so now I know I have this. So I'm going to do a couple of things. If I want pie pieces to each one of those, if we think about like the hexagon, I'm going to extract each one of these points here. And then I'm going to get the center point. And then I'm going to build up some triangles and then create like a hinge so that they can open and close.
yeah.
It's an angry computer.
Yeah.
That's crazy.
The CPU fan's not working properly, so
Oh,
it
no.
has to scream every time it does that. There's no way to turn it off.
Oh my gosh. And talk about like onboard, like it's probably like an onboard speaker that's just dedicated, so there's no way to turn it down. You're like without like physically removing the, oh, sorry. Yeah. Okay. So I'm going to deconstruct this brep. And that's not a brep because it's a curve. So that's not what I want to do at all. I want to come in a curve. I'm going to go to analysis, and I'm going to get the control points. And that'll give me the kind of corners of each of those. And then I can also do another point list here. And we can check to see what the order of those are, and I can't see any of that, so this will probably be that's way too big. Gonna bring these down. And we can see we have a weird looking 0 here, and that's because we have 0 and 6 are overlapping. Because we start at 0, and if we think about control points, like this is the start and the end of this curve overlap. So we have 0 and 6. And we can get rid of that by either removing one of them, but I don't think we have to do that for our data list because of the way we're going to start connecting these triangles together. So that's getting me my points. Now I want the center point, and I can do that by coming in here. There's a polygon center tool, and this runs a little bit faster. This is also an average. There's another way to do this. We can see we get a couple of different center values. If you type in average for mathematics, it'll solve the average of a set of points. And so we can put that in here, and we can see how it pulls it a little bit closer to 0 and 6. Because if you think about the center of any shape, like the average of all of its corners is going to be, one formula for the center of that shape is going to be the average of all of its corners. But as we can see, it's pulling it closer to this, our 6, 0, because we have 2 points in the same place. So if I go to col index, and the index that I want to col is actually the last one of this. If we remember, because I have wrap by default set to true, if I bring in my list of points, if the index that I want to call is -1, because if I'm wrapping backwards, it'll get me the last item in the list instead of the first item. And so now if I plug this into my point list, we can see I have a really nice kind of wrapping. I get rid of that overlap. And sorry, I'm getting a little bit messy here with the spaghetti. So bring that up into the average, and now we can see we have like a direct overlap of these two, of this average. So there's actually two different centers that it's finding here: the average of the polyline vertices, the average of the polyline edges, and then the last one is the centroid of the polyline shape. So a couple of these, there's technically 3 points. 2 of them are directly overlapping. And then the third one is the average of the edges that's giving us this like outlier. We don't have to worry about any of that because we just have this kind of cool math way of figuring it out. Like it's just raw math. I kind of like that more because math is really cool when it works. So now what I want to do is build up my, I don't know what I'll call them, my like aperture. And actually I think I like the rebuilt one a little bit better, just because it gives me less of the squishy points. Does everyone see kind of what and why I did that? Where if I just bring the loft straight over without rebuilding it, we get like this pinch point. If I rebuild it and then bring it over, I just get some stretch points. Okay, so we have our centers and our edges. So we're going to build up a couple of triangles around each one of these. That'll be like our flappers for now. And now I'm like super intrigued by the aperture one, so if anyone could beat me to it, I guess, yeah. Yeah. Well, again, you could look at the grasshopper form and like totally find like a script that's like 99% there, and then you'd technically have beaten me to it. So there's nothing wrong with using the grasshopper forms or other people's work, as long as you credit them for it. So I'm going to come into my surfaces. I'm going to come into freeform, and I can use a 4-point surface and only feed it 3 points, if we remember that kind of trick. And I'm wondering, no, it's not going to let me do that. And then the other thing that I'm going to do, because I have, I technically want to get these, I'm working with these outer points and my center point, is that I'm going to want to extract each one of these. So if we remember, if we go to list item, we bring our list over. Our default index is 0, and that index is going to correspond to the number on this hexagon. But if we remember that sneaky trick, we can actually add these out or extract out. So now this is our index 0. We're just going to leave default. So that's I, and then this is I plus 1. So 0 plus 1 is 1, and so on and so forth. So this is an easy way to kind of pull out each one of those discretely and get our, I don't know if that was the right word, discretely. Anyway, and then we also have our center. So now we can start building up. We're going to have 1, 2, 3, 4, 5, 6 different triangles here. So I'm going to start pulling these out. And I'll have 6. So the first one, I'm going to want to take 0 and 1 and the center. So there's my first triangle. Second one, I'm going to want to take 1 and 2 and the center. And then the third one, I'm going to want to take 2 and 3 and the center. And then for the fourth one, I'm going to want to take, where am I at? I'm at 3. You see how this would be so much more difficult if like all of my numbers were all stacked on top of each other if I was trying to do this for every single panel at the same time. 4, and then, you know, so on and so forth. So now I'm at 4, go to 4, and 5, in the center, and then 5, and 0, in the center. And that's some really ugly spaghetti string I've got going for all of these, but I think that'll be okay. Hopefully that is human readable. But now we have each one of these that we can then apply a different operation on. And another way we can kind of test this is, so I'm getting, instead of getting this list item where I'm just getting one, this guy, if I just flip all of these over, we should be able to see now I'm getting all of the panels on this surface are now going to be able to be transformed, which is a lot. Could actually go a little bit smaller, and I'm going to do that by coming up here and changing my U and my V. So here I'm going to say maybe like 8. And then here I'm going to say 50, maybe. Yeah, there we go. Just so that I'm not trying to wrangle so many different parts and pieces. But I guess before we do that, we still have a few things we want to be able to apply an operation to that. So in order to do that portion, I'm going to leave just that this one hexagon in here. We're going to manipulate it by kind of opening it up, perhaps. I think is the geometry manipulation that we want. So if we come into our transform tool, we have a whole bunch of things we could do to this geometry now, which is actually kind of fun. We could morph it. That would be weird. It could be fun. Splop is a fun tool. We're not going to get into that right now, but I just saw that. We could probably get into that a little bit later. I actually want to do a rotate. So we're going to do rotate an object around an axis, because we know our edges are going to be like our hinge, right? So between like 0 and 1 here, this line will act as our axis, and then we're going to rotate it about that, like so that hopefully it opens up. And we're probably going to get a whole bunch of geometry collisions and stuff because we're using this like free-form surface. There's ways that we can make this way more smart, like if it was a camera aperture or something like that. So we'll say rotate on the axis. And the only reason that I'm just perceiving that being a problem is that on the really skewed hexagons is that a couple of the panels might be able to interfere with like other panels just because it's not a perfectly flat uniform wall. But yeah, we don't want a flat uniform wall. So the next thing that I'm going to do is I think that I went and I grabbed my control points, and here I have, I'm going to say my curve. I'm going to make a curve container, which is what I should have done in the very beginning. And I'm going to bring that in. And then I can take this curve, and if I explode my curve, it'll give me all of my edges. So right now it's a single polyline curve. If I come into my curve, I'm going to go to division. No, it's not under that. It's under utilities, is explode. We'll bring that curve in, and then if we look in a panel, our list of segments here, I gotta quit typing P. Our list of segments, we get 6 line-like curves. So perfect. Those will function as our axis. Now we have 6 axes or curves that we'll use as an axis, and then 6 panels that we're going to then rotate around. So I'm actually just going to slide this all the way over next to the kind of area we want to work on, because now we have all of our panels and our axes in the same line, except I'm going to take another one of these list items, and I can actually just copy this one because it has I plus 5, or gives me all 6. So here's my segments. And I think the axis can be a line. So one thing I'm going to do is, just to make sure that I'm using the right one, is we'll see which one's 0. Yep. So there's curve 0, and here's panel 0. Or I guess we'll call it panel 0. So I'm going to take this in to the axes. I'm going to take this as the geometry to rotate. And now we can see, I think the default value is 0.5 pi. It is in radians, so we kind of want it to be a factor of pi. So I'm going to say pi times, 2 pi is like a full 360. So we don't want it to go any further than probably 0.5 pi, so that it's like sticking straight out. I guess we could make it like 1 pi. That's probably what we want. So I'm going to say 0 to 1.00, and had my alligator going the wrong way, 0 to 1.00. And that'll give me a slider with 2 decimal points that I can then put into my angle. And now we can see my little, it can flap its wings. So now we just have to repeat this 6 more times for the other 6. And we actually don't have to repeat everything. We just have to start changing which curve we're going to bring into which one. So I'm actually going to bring my angle all the way up here, because that'll be the same. So copy this. We'll see, where is this one on? Yep, that's the right one there. So we can say, hard line these in, angle to axes. And geometry I have to move down. Okay. So this will be a little bit boring for just a little while. That one there, that one there. And then I can take 2 into that axis. 3 will go into that one. 4 will go into that one. 5 will go into that one. Okay, so now we should be able to flex our angle here. If we're looking at this, right, that's what we wanted, right? So then, and we can bring that all the way out flat and make it interfere with the neighboring one. You look a little bit perplexed here. Oh, I'm missing one. Which one am I missing? That one. Geometry. Oh, because I have the wrong axis in there. I accidentally swapped my angle and my axis back there. So now they're all working, which is kind of fun. It's kind of fun to play around with. So now what we can do, we can apply this to every single one of those hexagons that we have, and then we can actually run our daylight simulation. How am I doing on time? I keep hiding the clock from myself.
2:40.
Okay, so we have, cool. All right, we're doing okay. So again, back where I had this list item, I can actually apply that to all of these, and we'll see if I don't crash my computer. Nope, that seems to work. And then for the angle, I'm going to bring this out. Oh, that's kind of fun. So now they're all kind of partially open. Is everyone Following along, everyone. Okay, cool. So now what we have, right up here where we're controlling the angle here with a numeric slider, we actually want to be able to do that dynamically. So we want to be able to, I'm thinking we'll kind of simplify this a little bit where for every one of our base geometry hexagons, we'll do an analysis to figure out what the solar radiation of it is. And then we'll add in some function or another piece of math that'll convert that radiation value to an amount of openness or closedness. And again, this is probably impossible to actually build in the real world. I'm sorry for that. We can do some kind of cool stuff to rationalize and make this a little bit better. But for now, we wanted to make some weird geometry, and we're still in the land of make-believe, so we don't have to worry too much. Great. So now we're going to come into our Ladybug tools, right? Because this is essentially, this is the key piece we want to be able to replace. So we want to replace that with our energy analysis of, where's my surface? Oh, geez. Okay. So I'll actually have to get, no, this will be fine because I can evaluate the original surface at each one of these points, and then each one of those points will give me a certain amount of radiation back. Okay, sorry. It's like, oh, we have our base surface, but our base surface actually is a whole bunch of little surfaces. Yeah, anyway, so if we remember from Ladybug, first thing we need to do is to open up our EPW map, maybe. Oh yeah, I forgot. The new Ladybug takes a little bit longer for the first couple of nodes. And it wants a Boolean toggle for true or false. So I kind of just came down to a new blank part of the canvas so that I'm not trying to compete with what we've already done. Set this to true. And for some of you, this is probably going to, Boolean toggle here. Right now it's set to false. The other one that we're going to just grab down before I do anything is import EPW. And wait for that to come in. So this is going to be asking for our EPW map, which we can just make I believe.
You can just do a panel.
Is that right? I think I'm missing one extra one here. I might be wrong. Well, we'll try it. Yep. We'll just make a panel because I think we can just copy that URL.
Yeah.
After we click this to true, it's going to bring up our map. Where do we want to be today? Should we be? Not now. Let's go to Spain. Go to Madrid. Copy link to clipboard. We can paste that in. It's not happy. So you can find EPW. Okay. So I think I'm missing this one. Yes. So I was missing this node right here, which is the download EPW. And then you bring your EPW file into your EPW file, if it lets you. Great, great. All right, we are moving. So now we have a good chunk of the information that we need so far. So we're going to come in here to analyze geometry, and we want to get incident radiation. So we'll drop that one out. For our geometry, we're going to use a surface. I forgot that it's not going to let me analyze the radiation at each one of those points, but that's okay because we can change our grid size to match the number of triangles that we have, and that should work out. Otherwise, what we could do is just take our flat triangles that we have for panels and analyze each one of those individually, and that way our output will be in the same data structure as our input, and that might be the fastest way to do that. So I will need a sky matrix. So I believe that one is in analyze data. Oh, sky matrix. Come on. Sorry, I'm having a.
Is it the cumulative sky matrix?
Yeah, visualize data.
Yes. Yes, thank you very much. A bit of a brain fart there. And I did click that, so it's thinking. The new Ladybug acts quite a bit differently than old Ladybug, but I think it's better overall. I've had an easier time messing with it, maybe. When it's not crashing. Oh, by the way, I'm going to do a file save as, so that I don't have to follow this along later. And I'm just going to call this Ladybug example 2. Great. So now I can take my location and plug my location in. And I think I've got direct normal radiation to my direct radiation, and my diffuse horizontal radiation to diffuse radiation. And that should be enough there. I can then bring my sky matrix into my incident radiation. One thing that I will need for sure is a Boolean toggle. Oh, here we go. Beep, 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 boop, boop. I'm an angry computer.
What's that? Oh yeah, it's brand new. I've been doing this since I got it.
Oh no.
Yeah.
Okay, so then I'm going to take each one of these surfaces. I'm going to merge them. So this is going to be a little bit of a tricky thing. So I'm going to merge each one of these into like their own data lists, or all of them into a single data list, so that then I can explode that data, then and input it for that move. Yep, we'll start from there. I'm gonna run out of time. I know that there's a smarter way to do this where we're not exploding each one of these, and that's what we're gonna look at next class, along with maybe another fun way to do this. So now we just have our flat panels. I'm actually gonna hide our rotated panels for now. If we can at least get through the analysis, I'll be happy. I'm just gonna open up let's check what this data structure is. Okay, so I'm getting, yeah, six surfaces for kind of each tree branch. So each one of these is kind of like its own hexagon, which is okay for now.
Did you forget that last surface?
No. Yes. I forgot that I'm going one more up. Because the merge starts at 1 instead of 0. Good catch. Thank you. So now I can bring these into my surface. This is my geometry. And this is also, actually I don't think I have to put that in for context. The next thing I'm going to do is hide all of this so that I'm not getting a whole bunch of annoying kind of double set. And then for grid size, don't know what the best one for grid size is. I'm gonna leave that. Guess, what do we have for distance here? Just gonna double check. Pretty much I just need one analysis, so that's 45 feet. So I'm gonna put in my grid size is gonna be like 50. And we'll see what that does. And with that grid size, it's pretty much just changing the amount of analysis points it's gonna have per each one of these panels. So if I set the grid size to 50, then it's only gonna have one analysis point, which is what we want. So now we can see the kind of weird shape of the weird kind of analysis we're going to get on this, which is what I wanted. That's why I drew it to be weird, because now we can change like the amount each one of these flaps based on that analysis information. But I'm going to have to be really careful to make sure that my data set is coming out the right way. So results, so I just want to make sure my data, and it's not, it flattened it because it had to flatten that geometry. So we're going to have to kind of rebuild that based on our data sets.